Hello everybody, I'm Lucas Pardue. I'm a protocols engineer on the protocols team at Cloudflare. I'm also the co-chair of the QUIC working group at the IETF. And today I'm here to talk to you about layer 4 3/4, fantastic quirks and where to find them. So just in case you don't get the reference to the number or the title, I'm talking about 9 3/4, which might make more sense to you. It comes from the Harry Potter world, but fair warning, if you did come to this presentation virtually to hear loads of Harry Potter jokes and puns, you might be sorely disappointed. Instead, I just want to talk about the number 4 3/4 and what does that mean? So we're going to ground ourselves in our familiar evergreen OSI model. We don't have higher than 7, well, we have 7, we don't have higher. We can't make the joke about 9 3/4, so I'm going to pick a different number, 4. This layer model is sometimes called a layer cake or protocol cake or whatever, but it doesn't matter. As the only thing that's important to remember here is that the cake is a lie. It's detached from the reality that you and I and the audience out there operate at. It's a work of fiction. Like all good fiction, it can be remixed and you can pretty much do whatever you like with it and nothing bad happens. So it's kind of nice. I'm just going to turn the layer cake I had previously around. Did you notice that? Probably not, because the figures are too small. Doesn't matter. But it got me thinking. Looking at it in this order, the other way than we might normally use it, reminded me of something else. So I want to introduce myself again. I'm Lucas. If you know me, or if you don't, I'm from a place called Cardiff, the capital of Wales. You might know it as the hometown of Shaking Stevens, the most successful singer in the world, one of my favourites. But anyway, layers, yeah, they reminded me of Cardiff Central railway station. In this image, we see like an overhead view of Cardiff Central Station. We love trains, don't we? And if you look closely, the immediate similarity here is that from top to bottom, the train platforms are numbered 1 through 7, just like my cake. What do you think deeper than just that surface level observation and more abstractly? Train lines and stations are kind of a good analogy for the legacy communication stacks that we have. Hundreds of years ago, some old people that you'll never meet had some ideas and lofty goals to improve the movement of things from A to B. They came up with designs, they made design decisions that were well-intentioned, they laid foundations for future generations, and everything was happy and successful. Those train tracks provided structure for movement, and we designed vehicles that could move across them, carry various kinds of things, and scale out to changes in what we were carrying. But sometimes those plans don't quite really play out as we want, or the way that people had hoped. Sometimes we want to extend things further, change stuff, that's life. But, we can't just rip out train tracks and smash down platforms, can we? If we go back to the OSI model, look at this layer. Like I said, you can do anything with it. It doesn't really matter. It's this abstract thing that can't help, but it is also completely useless at the same time. I could just take out layer 5 and put it in the bin, and no one would care, nothing bad would happen. You can't do that in the real world, right? Well, look again at Cardiff Central train station. Look closely at layer 5. No, platform 5 even. It's not there. It was removed in the 1960s. These folks were well ahead of OSI in just, removing stuff that wasn't used by anyone. But what about if you want to extend behavior, not just take it out? Cardiff Central Station did that too. They added a platform 0, where I used to catch a train to work occasionally. It does exist. But you can also see this example. Not platforms, but lines. They crammed extra lines in between platforms. Who could possibly use that? There were use cases for traffic to travel through that station that didn't need to stop. It just needed to be routed through. It's not going to serve the public or the people using that station, but it serves a different kind of audience. Who might that be? And now you might just be all confused by these analogies, or maybe laughing at them. I don't know. I can't see you. I can't engage with the audience because I'm stuck in my house using the internet. But what I'm trying to illustrate with all of these things is pretty straightforward, right? We only need 2 things and maybe the 3/4 between them. That's all that matters to us. And those familiar with Harry Potter will just know that the obvious thing to do in this case is to put those things together and just run as fast as you can at them and see what comes out. So that's what I did. I threw away all the other layers, just concentrated on layer 7 and layer 4. Some of you might balk at the idea that layer 3 is gone. The IP is really important if we're talking about the internet, right? I won't argue there. Our company motto is helping build a better internet. It is important, but for the purposes of end users who I like to focus on, they don't care. was my argument. We're talking about scale of users, people who interact with the internet and the web. They don't use IP addresses. They access services or applications. So I don't want to spend any mental energy on thinking about layer 3 for the purposes of this talk. Instead, I want to focus on the other layers. But also it's interesting to think in the context of the IETF or other work that's going on that's reducing the importance of IP address, both from the client and the server perspective, and trying to minimize the amount of IP address, say, collection, in order to improve privacy for people on the internet. So we have the rise of oblivious services online, ways of constructing components that can work together across a distributed system where we still have security and confidentiality, but we're less reliant on IP for those things. It's good, it helps routing, but we don't need anything more. The reason I want to focus on layer 7 and layer 4 is because it's my day job. Like, I have to just work on these things day in, day out. On the protocols team at Cloudflare, we work on these protocols like QUIC, HTTP, TLS. You might know us from the IETF or other standards bodies that we engage with to try and keep pushing the edge of innovation or address things that come up in real world usage at scale. But our team at Cloudflare is responsible for the components to provide those interactions. We provide reverse proxying at Cloudflare's edge, mainly for the web and HTTP, but there's some kind of HTTP use cases that need to punch down through the boundary of layer 7 into stuff below them in order to get their job done, to provide a different interaction model, say. So just keep that in mind. Anyone who's familiar with kind of proxying, intermediation, CDNs, etc., knows that adding this capability between client and origin servers provides like ample opportunity to improve the speed and the security, the scalability, the reliability of them. All things are very important. Maybe not super glamorous, but they end up in improving real world metrics that people care about, not because they're metrics, but because they improve the behavior of people's actual usage of services on the internet. So we operate this edge at internet scale, and that helps lots of users, but it also helps customers, people who run those origins, because they don't have necessarily the time, the expertise, the skills to stay up to date with evolution of web and internet protocols. So for us, scale also means the long tail of origins that maybe can't or won't migrate or evolve. And the intermediation ends up in a very interesting case of trying to adapt between old and new protocols, which is maybe a source of some quirks. But beyond that, we're also responsible for a product called Spectrum, which focuses on other less web-oriented protocols. So primarily in the realm of layer 4, and we support TCP and UDP there. We do a few layering violations upwards in order to provide some added value for people. And we also provide some specialized support for specific protocols like SSH, RDP, and Minecraft. I never really looked at Minecraft until this talk, say. There's different protocols of Minecraft. Did you know that? Like, did anyone know that? The differences here is that between Java Edition and Bedrock Edition is that one uses TCP and one uses UDP. Like, if you thought RFCs and IANA were fun, or maybe not fun, but fun for some kind of definition, I'd encourage you to go and look at these wikis to see how much documentation is on there in terms of versioning and different facets that maybe are bread and butter and you wouldn't possibly expect of a Minecraft community. So we need to challenge our preconceptions of this stuff, even if it's not in a standards world as maybe some of us use day in, day out. And one measure of a serious protocol might be that it has a Wireshark dissector built in. I thought QUIC was the only game-related protocol that was serious. But no, there's dissectors that you can get for Wireshark too. But people want to spend some time investigating, debugging, maybe reverse engineering how these things work because they have an interest or a real need. So again, it's something to keep in mind. But we talked a bit in the abstract, and we took a minor diversion to Minecraft. I want to dig deeper into HTTP because that's what I love, and that's what I spend a lot of my time on. This conference is called Networking at Scale for Transport, and I want to pick at the definition of all of those things to maybe challenge some preconceptions. And for me, the transport is mainly HTTP. It means Hypertext Transport Protocol, right? Well, no, it doesn't at all. It's Hypertext Transfer Protocol. And Mark Nottingham at IETF 99 rightly called this out. He said, and these are minuted, you can check, that Roy Fielding knows whenever you call it Hypertext Transport Protocol. I won't name any names of who said that, but you can probably work it out yourselves if you go and review those minutes online. So, let's get a bit more serious here. It's not a transport protocol, HTTP, but it is used for a very wide range of use cases, either as a substrate or an application, or effectively manipulating HTTP into be something a little bit different. So before we get into those things, I just wanted to take a look at maybe HTTP in its conventional usage on the Cloudflare edge. We operate something called radar.cloudflare.com. It's a public source of up-to-date trends and insights from our edge, covering not just HTTP, but a wide range of things. Here's a screenshot that was taken on April 27, 2022, showing effectively our view of traffic for the 30 days prior. And that's traffic to the CDN edge, not other services that run on our systems. The notable stats here I'll point out are that most of this traffic is encrypted HTTP2 and HTTP3. 99% of this traffic is HTTPS. Only 9% of the traffic is HTTP 1.1. And so of the remaining fractions, if you're doing your maths, like a tiny, tiny fraction must be plain text HTTP 1.1. So we hear quite often that the way that H2 and H3 have evolved, they hurt people who want to debug these things themselves, write their own servers or use Netcat and just write directly into port 80. Those people are 100% right, but most of what we see are these binary protocols that have additional behaviors and rules and requirements that are not the same, and they're not easy to debug. So that's what I want to focus a bit more on. And I want you to keep in mind like how these things might actually look like on the wire. They're not streams of ASCII text flowing back and forth. They're collections of streams that contain frames that are binary encoded that are going back and forth. We can't spend all day digging into this stuff. It was covered maybe briefly by John's talk earlier, and how streams are provided by the QUIC transport layer. But streams are also in HTTP2. HTTP2 is a layer 7 protocol, but it provides these kind of transport-like features. It's kind of really annoying. And that's maybe some of the motivation that made us go to HTTP3 for the better. But we have to live with all of these things right now. And maybe we have to map between them. But this is kind of what they look like on the wire. There's a lot of different ways to look at them. But just keep in mind, these things aren't simple to look at. Go back to some data here. We have this kind of worldwide global view of HTTP3 traffic share, which is interactive and really good if you want to visit the link and play around and maybe see if your country's in there and how much of the share of all HTTP traffic that we measure is just HTTP3. We've got a heat map that shows the popular areas, and from dark orange and then light orange is less popular. So it's cool. I like this view. The right-hand side is the top 10 list of countries, and those answers might surprise you. Maybe you're expecting something different. Let me know your opinions there. But looking back on HTTP3, RFC 9000 came out in May last year, so it's been around about a year. I wrote a blog post at the time and said, at that time we were seeing around 12% of traffic using HTTP3. If I was to look at radar today, the average globally is more like 24%. And in some countries that can rise to 35%. So we're seeing over the course of just 12 months, some clear progression. I won't go into the reasons why. We hope to follow up with some more public communications about the data that we're seeing here, but I just thought it would help to present a high-level view of some of the long-term trends that we've seen between the period of May 2021 up through April 2022. So on this chart, what we have is global data for HTTP requests broken down by HTTP version. The purple line is HTTP3. It started off a bit low, even below HTTP 1.1 usage in May 2021, but soon after RFC 9000 came out, it overtook it, and it's continued to grow, which is great and interesting for people who have spent years defining standards in the IETF and seeing them being deployed and successful. This is good. It's still not quite as high as HTTP2, but who knows why? Who knows when those might change? I think there's always going to be a world for TCP-based HTTP. Maybe H2 will continue to rise or fall. It'll be very interesting to see how things progress over the next year. Maybe I'll come back next year if this talk is successful. But let's break that out slightly into separate browsers. So just looking at Chrome, Firefox, and Safari here. Again, we have HTTP3 in the purple, H2 in the red, HTTP 1.1 in the green. HTTP2 is clearly the most popular across all the browsers, but H3 has been growing and at some slightly different rates. Again, there's possibly reasons here. I think in the Firefox example, the jump in increased usage of HTTP3 aligns with the rollout of Firefox that enable that by default. We're going to see more and more user agents enabling these kind of things by default. And so at some point, maybe the proportion of protocols will depend on Cloudflare customers who configure their zones or their traffic to enable or disable HTTP2 or 3. Just to give you an example, Cloudflare free customers have HTTP3 enabled by default, but other customers don't. We just give them the option to, just in case they're a bit more risk averse. We've been running this in production for 18 months or so now, and everything's been great. We have room to change things and continue to iterate. QUIC's brilliant for those things, but so far everything's good. And if we just look at HTTP3 traffic and look at maybe how those requests break down by browser, no surprise, if you look at maybe just market share of things, Chrome is the largest market share. That's on radar.cloudflare.com. I don't have those on these slides, but you can see a kind of progressive growth. This isn't so useful, right? It's some lines. Let's look at a stacked view of percentage share. We can see in the yellow, Chrome is still the biggest, but there was a slight drop of the share of HTTP3 traffic around that May to July timeframe. And we can see the growth and the variation more clearly of other browsers in that case. If we just take Chrome out with a picture, we can focus on those other browsers a bit more. You can see some curious interaction between Edge and Firefox there, kind of competing for who wants to do the most HTTP3. That's kind of interesting. We've got Opera in the mix too, another Chromium-based browser. That might not be as popular at the front of people's minds, but it's there. It's using HTTP3. We've got Safari too, showing maybe a different pattern. Again, we hope to follow up on some comms that can dig into these details a bit more. Browsers aren't the only thing, right? We have other kinds of clients. We have Facebook. Their traffic pattern is a bit different to others. Not sure why. Maybe some people here can explain that to us. And we also have non-browser traffic, like bots, people who are powering the internet, not via human touch directly, but doing things like APIs or crawling the internet. So we have things like Google, Apple, Facebook, Bingbot, all don't really show us much HTTP3 traffic, but they do show interesting variation in HTTP 1.1 and HTTP2 usage. I'll try to reach out to a few people to understand maybe why these traffic patterns are happening. It'd be really interesting to get a response. Google have said maybe that for Google Bot, the decision to use H2 is based on client or the crawler performance and the server load, these kind of things. I don't quite know, but it's very interesting to see. So that's it for the data. Let's come back to other things. We've talked about this binary framing. My argument here would be that we just need to focus on HTTP2 and HTTP3 because that's where we see the most traffic and that's where we have the least successful amount of debuggability, right? Maybe you disagree. The text-based HTTP has pedigree in providing quirks for us. We've seen some recent new examples, the so-called like request smuggling attacks that are there. Despite the protocol being around for decades and well known, there's still opportunity to do fun and quirky things. But despite that baggage, it's pretty well understood by at scale a community of people who are able to work with HTTP just as a thing that they pick the spec off the shelf and use it and apply it. Maybe good, maybe not as good because it's hard. But I would argue that HTTP2 and HTTP3 constitute the majority of the web traffic, and that we have yet to really fully characterize their quirks, the way that they perform well or perform badly when things go wrong. So let's look at some examples around that. We have some tooling that's out there that helps us analyze things. We have tools like H2spec and H3spec that can emulate clients and test whether servers are compatible with the specifications. Things like H2load that can do load testing. A lot of load testing tools don't actually support HTTP2, let alone HTTP3. So if we're just measuring can an application server take a load, that's okay, that's one thing. But if we're measuring more like traffic balancer, load balancer type traffic, it can be tricky. Maybe you develop some tools that kind of do these things for you. But again, how well can the community beyond us actually characterize their servers or their clients? Clients behave differently too. They might not follow the RFCs as they need to. How do we test in the reverse direction? When things go wrong, we have stuff like netlog or qlog, can maybe provide some details. Not always, they're different. Do they go to the right level of information? Sometimes yes, sometimes it's too much and it crashes your browser session when you try to open it in the net tools. I don't know. We trying to presented another option earlier. That might be something that gets community traction. It would be really good to just improve everything in general, not just for the IETF people, but as a community, to improve the knowledge and to make these things much more user accessible, to know where to go when things go wrong. An example of that is this error that some of you might have seen. I don't want to pick on Chrome, but Chrome provides errors like this that I don't find personally helpful. So if you've seen one of these error messages, you might have thought, how do I fix it? I'll Google it. I found this answer, flush the speedy pockets. Have you ever done that? I don't know what that means. Maybe it works. Maybe you've seen one of these messages, H2 protocol error. How do you solve that? You Google it, it says turn things off and on again. Like, is that funny or is that just a bit sad? It seems sad to me. Maybe you got a QUIC protocol error, one of my favorites. What does that mean? Again, Google this one. One example of some advice I found online was to contact customer support at Google. I don't know if you ever tried that. I don't know if the bug tracker is customer support or it's something else, but I had an issue around error log reporting and I'd like better granularity and I opened an issue. I got a prompt reply. It was great. We had a good discussion on this ticket. But sadly, people have different priorities and that work is still outstanding. And every now and it comes up again. Oh, we've seen this generic error. Can we get something better? I'd love to be able to improve that. I can't do it myself. I don't know if anyone can maybe do this. But that's just Chrome. There's other browsers, there's other user agents that have these kinds of errors. How can we make just the person on the street able to understand what they are and how to feed that to people who might be able to investigate and fix them? One example I've got recently, I'll call it Lucas is malformed. In H3, every request has to have some mandatory pseudo header fields. And if they might have something missing, it's an error. So malform request, the server must respond and reset the stream with a specific error message. It might send a response code prior to that reset stream, but it should do that by the letter of the law of the RFC. So I did some testing, 10 different servers on the internet. These are ones I know all use different server implementations. So it's trying to test the diversity of approaches. So just out of these 10, 4 returned 400 bad requests. One returned a 405 method not allowed. I thought that was quite funny because there was no method. So I don't know what method it thought wasn't allowed. 3 sent a reset stream, which is what the spec says to do, but they didn't use the error code that the spec said. And then 2 sent just the application layer connection closed with the correct message. So it seems no one's strictly following the specification, and that gets a bit annoying if you're trying to debug these kinds of issues, because if you just see a generic error occurring or something like, how do you find the root cause of the problem that you're investigating? This takes engineers time. It's probably okay if you want to get really into error code reporting, but it's not very user-friendly. And I'd love to find a better way for us to diagnose problems like this. Something else that happens, not just cryptic errors or functional problems, is performance or behavioral, temporal actions. We had something a few years ago around HB2 denial of service. The community did a great job of reporting these responsibly and giving vendors or owners of the software an opportunity to assess whether they were vulnerable to these kinds of different behaviors that could trigger denial of service in their implementation. We got the fixes out. We did a great job. One of those was CVE 2019-9512. This is just one of them. There's a few others, but this one was about ping floods and denial of service. So some implementations were vulnerable and some implemented mitigations to avoid floods of ping frames in HB2, which is great because we have this protocol called gRPC, a layer 7 protocol based on HB2 that uses ping frames. There's one example of a Go client who implemented something called BDP estimation for performance. And they say the idea is simple. Just you send a ping frame every time you receive data, and you can measure BDP from that. The problem is this leads to a lot of pings, and maybe you can see where I'm going with this. Then we'll add into the mix that Rust's hyperlibrary copied that design, the BDP estimation design, and called it adaptive window. And so if you have Rust hyperclients out in the wild at that time that implemented or enabled this adaptive window feature, they found that with some servers, they were getting connection closes and they couldn't figure out why. But after this was reported and we investigated a bit more, all on GitHub on those issues, you find that, yeah, there was a problem. And if you turned off adaptive window, the problems went away. And so working together, we're able to find some way of kind of interacting with servers differently and to reduce the aggressiveness of the pinging. And the upshot there, actually, was that the performance improved. Not only did it not upset the server so much, but the client got a better experience at the end. So that was great. Just to use a different example, we have something called speed.cloudflare.com that was launched in May 2020. The intent here is like some other speed tests that you might be familiar with to measure download, upload latency, and jitter on the internet. So this went out and people liked it and they used it, but soon after we started to get a small number of reports that sometimes the upload speeds that were reported were very small or underreported for what the users were expecting and were seeing when they did other kinds of upload tests. This seemed to happen more with high bandwidth on the line, so cases where you might have fiber in the home. We dug into this a bit more. The speed tests were performed by browser JavaScript. Browsers prefer to use HTTP2. If we force things differently to use HTTP 1.1, we were seeing that the upload was working a lot better than the HTTP2 case, which was kind of interesting. So we looked into things. And again, this was a HTTP2 flow control problem in the end. And we were able to basically use the information we were collecting from the public to improve the Nginx implementation. And we've blogged about this, and it's kind of got a lot better performance all around just by increasing the diversity and scale of people. This was a bug that had been there for as long as it existed. And it's a really easy bug to fix and spot when you know what you're looking for, but it lay there as a latent issue, which is kind of interesting to me. So it makes me think, when we're measuring speed and performance, what are we measuring exactly? We want to focus on the layers below HTTP, layer 4 or layer 3 if you want to pretend that does exist, it doesn't here. And as long as those things are doing well, everything's great, right? But it's not true. HTTP can still be bad, like I've just shown you. So this is kind of some of the motivation for us to submit to the IAB workshop about measuring internet quality. We wrote a submission called Lower Layer Performance is Not Indicative of Upper Layer Success. Not just focus on that one issue, but to try and think more about end user interactions with the web and how different things affect how things actually work, not just basic ping and bandwidth measurements, but web application use cases. So that latency and jitter are fundamental. We're seeing in the IETF, the IPPM working group, working on some new ideas about testing responsiveness under working conditions. And so if you thought all of that was hard and funny or whatever, I've got some bad news for you. Like as Snape might say, life isn't fair. As John presented earlier, HTTP and QUIC are providing a new substrate, new evolution. Things are going to get more complicated for us, and that's an opportunity for new quirks. One example is the HTTP datagrams and the capsule protocol, which the Mask Working Group has just finished working on. This opens the door to a lot more exciting things. It works by taking the QUIC datagram extension and mapping it into a new kind of semantic for HTTP, which is cool, but also a bit scary at the same time. That might help lead us to a world where everything is carried over QUIC in HTTP3, the kind of UDP 443, all the things, using these capabilities, which might support use cases like proxying UDP over HTTP, proxying QUIC over HTTP, either HTTP2 or HTTP3, other things like web transport or media over QUIC. There's a lot of excitement here, but also a bit of concern for what quirks might emerge. When you talk about QUIC and QUIC, that's the natural thing that I always think about when you can layer protocols on top of protocols. Let's get as complicated as we can. In this case, you can combine multiple proxying and tunneling and all stuff together. We have layer 4 and layer 7, and layer 4 and layer 7. It's all great. It all comes to adding it up and dividing by 2. What do you come out with? Layer 4 3/4. I want to conclude the talk by saying this is layer 4 3/4. This is where the quirks are. This is the intersection from layer 7 to layer 4. And if you're more an application-oriented person, you're going to have to start thinking slightly below into the framing and the streaming layer, or the interactions between things. And if you're at the transport layer, you need to start thinking about punching up into the higher layers, especially with things like QUIC, which incorporate more application or TLS contexts. This kind of thing, it's great, it's exciting, but it's not so simple. And that's what it is. But the point I want to make with this talk is to shine a light more on this, kind of come up with some calls for action, to think maybe how can we work as an internet community to be better at finding the quirks, be better at fixing them. You know, we know where they are, but when we find them, do we know what they are? What things do we need to do to invest more effort so that we can scale out the ability to find and fix these bugs? We have developers, we've got sysadmins, SREs, engineers, so the whole world of people who use these protocols every day, who maybe don't have the skills, the knowledge, the information, the tooling that can help them just get on with their job. When things go wrong, they know what to do. We have some decent tooling already, but we can do a much better job, in my opinion. So I think we can build or take some next steps for a positive future for innovation. And I'd love to hear the community, see if we can work together and do something better. Thank you very much for your time. I'm Lucas Pardue, and I like protocols.